So today we're on to 5C in kinematics, and up here I'm going to go through 5C.1 and 5C.2 because 5C.1 is quite easy. We'll polish that off pretty quickly and that'll allow us to get into 5C.2. It's important that we do have a read of this. This is a recap of kinematics, right? So we've done a fair bit of it when we did the applications of calculus, but just reintroducing you to, reiterating the different functions. So displacement, S of t, velocity, V of t, and acceleration, A of t. And so if you differentiate displacement, you'll get velocity. So therefore, if you integrate velocity, you'll get the displacement function. That's the link that we're making. And then we've got that stuff about distance, the difference between distance and displacement. I think we're pretty good with that. Changes direction, like an object changes direction when its velocity sign diagram changes sign, and then some points about speed. So that's a summary there of information we need to recall for kinematics. Okay, let's get straight into 5C.1. And what we have here is velocity time graph. So this is like from year 10 physics. This is probably where you first learn it. So if you haven't done year 10 physics, it might be new to you. But all we're doing is area under the curve of a velocity time graph. The area under a velocity time graph is the distance travelled, or we can call it the integral from A to B of V of t, right? If velocity, if V of t is the velocity function. So we're given a velocity time graph here, and we're asked to find the total distance travelled. Okay, we want to know how far has it travelled in total. So I'm going to sketch the graph up here, and then we'll break it into a couple of components. All right. So if this is its velocity, right, and this is its time. When it's above the x-axis, that means it has positive velocity, and so by nature, we suppose that's moving to the right. And then when it has negative velocity, when it's below the t-axis, it's moving to the left, right? So if we're going to calculate the total distance, we need to add up the area for all of these parts and add them together. So we're just going to break it into a number of shapes. We'll go triangle there, rectangle here, triangle here, and then a triangle here. And then we just need those measurements. So this is 2, this is 6, this is 10, and this is 11. Hang on, I'm drawing that properly. That's 11. No, it's not. That's 12. So that can be 13. All right. And then as far as the height goes, this is 4, and this point here is -2. All right, so let's break them down into those shapes then. We've got shape A, shape B, shape C, and shape D. So A is a triangle. It has a base of 2 and a height of 4. So its area is going to be 0.5 times 2 times 4. 4. B is a rectangle. It has a base of 4 and a height of 4. I'll keep going. 4 times 4, 0.5 times 4 times 4. Three and down 2. (28 to 31). All right, so just some basic geometry, right? Working out the areas. Area under the curve, all right, of the velocity time graph tells you the distance. So over the first 2 seconds, it travelled 4 meters. And we can see it's accelerating because it's getting faster and faster. And then between 2 seconds and 6 seconds, it's travelling at the same speed. Its velocity is not changing. Okay, then it starts slowing down. So it's braking, it's starting to slow down. Here it has a velocity of 0. So after 10 seconds, it's stationary, but then it has negative velocity. So that means it starts moving back the other way. Okay, so just picturing that in your mind, what's going on. and then we've calculated how far it's moved over each interval. The total distance it's travelled is 31 metres. That's the sum of all the areas under the curve. Okay, on to part B. It says, what's the total displacement? All right, so the total displacement means it's moved to the right and then it's moved back to the left. How far is it from where it started? So we can see it's moved A, B, C, that's moving to the right because it has positive velocity, and then it's moved D units to the left. So all of these are moving right, and then this one's moving left. So we've moved 4 plus 16, 20, 28 metres to the right, and 3 metres to the left, takes us to a displacement of 25 metres from the origin. All right, we're 25 metres to the right from the point of origin. Okay, and then part C, what is the significance of the total area above the x-axis? So if we just go A, B, C, what's the significance of that? Well, that's how far it's moved to the right, okay? So all of the area above the x-axis, how far it moves to the right. All of the area below the x-axis, how far it moves to the left. So A plus B plus C is 28. The particle, the object, whatever we're talking about, moves 28 metres to the right. From 0 to 10, times 0 to times 10. Excellent. Okay, so that's 5C.1. Do people want to stop there and have a go at that exercise? Or should we keep going?
Keep going.
Keep going, excellent. All right, give me a sec and I'll just spin around actually. Okay, so 5C.2. All right, so now we're making a link between velocity and displacement. So I've got written at the top there, recall if the displacement, the derivative of displacement is velocity, therefore the integral of velocity is displacement. The change in displacement is given by the area under the velocity function. And sometimes we might need to draw a motion diagram. Okay, here's v of t, this function here. T squared, take 4t plus 3. Part A says, draw a sign diagram of v of t, and hence state time intervals when it changes direction. So we just want to draw a sign diagram of this. Now the best way to do it is just going to be graph it and draw the sign diagram from there. Okay, so graph, put that in your calculator, draw the sign diagram. I'm looking at that and going, that's a quadratic, we can factorize it. T take 1, t take 3. All right, and so the roots are 1 and 3. Now remember, when we're talking about kinematics, we only consider positive values of time, right? So we're starting here, and we've got roots at 1 and 3, and I'm looking at this quadratic, and it has a positive a value, so it's above, below, above. All right, so that's the velocity sign diagram. You can get it straight from the calculator. You can perform the algebra as I've done here, it doesn't matter. That's the velocity sign diagram. Okay, part A, draw the sign diagram, hence state the time intervals when it changes direction. An object will change direction if its sign changes. All right, so here we're moving to the right, we have positive velocity for the first second, but then we have negative velocity, so we start moving to the left. So we can see it changes direction at t is 1 and t is 3. Okay, part B, calculate the integral from 1 to 3 of v of t and state its significance. So this is something, like here in this exercise, we should just be using our calculator if we can. You can do it manually, it's just going to take longer. I'm going to get mine out. And so I'm just going to run that, and I'm just typing in integral. Here's the velocity function, doesn't matter what form you put it in. All right, option calc integral. We've got x squared, take 4x plus 3 from 1 to 3. All right, so I've evaluated that, and I've got minus 4 on 3. So the value of that integral is minus 4 on 3. Now, area under the velocity curve is distance. All right, so it's moved 4 on 3 units to the left. And of course we expect that, because between time is 1 and time is 3, it has negative velocity, which means it's moving to the left. All right, so that's what it evaluates to, the significance between the object, the particle. What are we talking about? We're not told. Object moves 4 on 3, 1.33 recurring meters to the left. Okay, part C. Find S of t. Find the displacement function. Well, the displacement function is equal to the integral of the velocity function. Okay, the displacement function is equal to the integral of the velocity function. So it's going to be the integral of this one, t squared take 4t plus 3 with regards to t. So that's going to be t to the 3 on top of 3, take 4t squared on top of 2 plus 3t plus c. And you can simplify, that term will simplify. Don't forget the plus c. Okay, good. And then we've got parts D, E, and F. So we need to determine the displacement after 5 seconds. So that means S of 5, all right? It wants us to find S of 5. Oh, sorry, part D. Draw a motion diagram over the first 5 seconds. All right, so where we're up to now is we're going to recap motion diagrams from APSA calculus. It's pretty much the same skill, but there's one small variant one. Now, for a motion diagram, you need where it starts, where it ends, and any places where it changes direction. So for us, we need the displacement when time is 0. We need the displacement when time is 5, because we've said over the first 5 seconds. And then we need its position, we need its displacement where it changes direction. Well, it changes direction at time is 1 and time is 3. That's the relevance of that. We've already done that, right? So we need the displacement at time is 1 and the displacement at time is 3. And so if this is the displacement function here, all we're doing is putting these numbers into this equation and evaluating. Now the fastest way to do that is going to be to graph this function and just G-solve them. Now the thing is, we can't put this plus c in the graph, that's okay. We'll leave it out, we graph everything here except the plus c, and then whatever it evaluates to, we just put plus c on the end. All right, because it's going to be that number plus c. We can't put that in our calculator, we'll put this part in and just G-solve it. So for instance, when I put 0 into this equation, that's going to 0, that's going to 0, that's going to 0, we're just left with c. All right, its initial position is some C. All right, some number. I'm going to graph it and G-solve those other pieces of information. So we've got x to the 3 on top of 3. Take 2x squared plus 3x. And then I'm just going to trace. I want to know when time is 5. Or I can't read it, 6.6 I think. 6.6 recurring, so it's that 20 on 3, doesn't matter what you write it as. 6.6 plus c, and then when time is 1, 1.3, so that's 4 on 3, and when time is 3, 0, so c. Very good. So how have I generated those? All right, I've graphed this function, and I'm just pressing the trace button, and I'm typing in when x is 0, when x is 5, when x is 1, and when x is 3. All right, what's the corresponding y value? Y value 6.6, y value 1.3, y value 0, y value 0. All right, very good. So I'm going to clear a bit of space here. That's just from the previous question, so I can draw the motion diagram. So for a motion diagram, we need an axis, right? And on this axis is the distances we're interested in. And so I'm looking here and I'm going, what's the furthest that goes to the left? What's the furthest that goes to the right? So the furthest point we have to the right is going to be this one. That's the largest number, right? 6.6 plus c. So I'm just going to plot that there. All right. And the furthest point we actually have to the left is c. All right. It's c units to the left, so I'll put that here. And then the other point of interest is this one, 1.3 recurring plus c. So I haven't even drawn it to scale. The scale is not relevant, right? The purpose of the motion diagram is to allow us to calculate the distance in a moment. Okay, so this is how we draw a motion diagram, right? We have the axis, and I've just taken the points of interest from there. It starts here. When time is 0, this is where it starts. All right, after 1 second, it's here. All right, at 1.3 plus c. It then changes direction, and it gets back to c when time is 3. So it's moving to the right and then to the left. Okay, positive velocity, negative velocity. All right, and then after 3 seconds, it changes direction again, and it moves to the right until we get here. All right, so that's the motion diagram. That's part D. Now, drawing a motion diagram, like in a test or exam, it's not an essential skill. Rather, it's like you can use the motion diagram to aid your answer, but it's not something you have to do. There are other ways around it. So I might make a link for you in a moment. So for instance, in part E, where we've got determine the total distance over the first 5 seconds, how far has it travelled over the first 5 seconds? Well, what we can see is it's travelled 1.3 units there, plus 1.3 units there, plus 6.6 units there. So its total distance is 1.3 recurring plus 1.3 recurring plus 6.6 recurring. Okay, I'm just adding up the distances between the points, right? And we can chuck that in our calculator. So it's 4 on 3 plus 4 on 3 plus 20 on 3. What's that? 28 on 3. Yeah, I'm happy with that. Okay, so that's one way we can do it. All right, and that's the purpose of the motion diagram. Another way we can do it is to go, well, I want to know how far it's travelled in total. So the integral from 0 to 1 of v of t, okay, that's going to be how far it moves to the right over the first second. And then what I'm going to do is I'm going to add the negative integral from 1 to 3. Why the negative integral? Because it's moving to the left, because it has negative velocity over that interval. And I want that to be a positive distance. I'm interested in adding all of the distances together. And then lastly, it's moving to the right from 3 to 5 of v of t. All right, so you can just put something like this in your calculator as well. You don't need to do the motion diagram and perform it like that. All right, it's going to end up with the same answer. Okay, lastly, determine the object's displacement after 5 seconds. All right, and we've used that here. Okay, part F, S of 5, the displacement when time is 5 is 6.6 recurring plus C. All right, how do we feel about that skill? Hopefully seeing a bit of overlap with apps calculus. Let's get into 5C.1, 5C.2. Wednesday's lesson will just be dedicated to 5C.3. So see how much you get done today, but there will be some time on Wednesday to do a bit of C2 as well. All right.